Real-world scalable entity resolution. I am Nick Bates-House, Chief Architect at Tamer. Welcome to part 5 of our 5-part series. In the previous parts, we talked about why entity resolution at scale is hard, and as measures of success, we observed that we were able to deduplicate or perform entity resolution on a 500 million record dataset representing the entire population of the United States with duplicates in under 3 hours and for under $300 on commodity scale-out infrastructure. Furthermore, we were able to show that we can perform a 1% delta on that 500 million records quickly and with stable IDs. In part 2, making the easy part cheap, we talked about how to address obvious matches and obvious non-matches, and as a measure of success, we observed that we were able to reduce those 500 million records down to fewer than 1 million pairs that the machine learning would need to look at. In part 3, making the hard part scale, we looked at how to apply the machine learning to those 1 million pairs. We looked at signals, similarity, clusters, and consolidation, and as measures of success, observed the overall efficiency, but also that the dollar cost for different sizes of scale-out infrastructure remain equal across those different scales. In part 4, effective learning, we talked about the learning workflow, including the bootstrap, refinement cycle, and validation phases. And as measures of success, we observed that we achieved a model with excellent accuracy with fewer than 1,000 labels, and we were ready to deploy into production in under 2 weeks. In this part, we'll talk about coping with change. We'll start with the definition, what is change and what does it mean to cope with change, then talk about the change processing workflow and some measures of success. So what is change and what does it mean to cope with change? Change naturally involves changes to data. The most common form of change to data is that values in the data are modified. This may include changing values that are important to machine learning, for example, identifying columns. This can happen both in data sources. It can also happen through data curation. But it's not just individual values on individual records that may be modified. We may add entire records, we may remove entire records, and we may add or remove entire data sources that may contain millions of records all at once. So that's a lot of change to accommodate all at once. Change also involves changes to context that may be changing business, legal, or governance requirements that change how we measure the accuracy or how we measure the quality of the output of the system. It may also involve changes to data processing infrastructure that change the way we're computing results or require transferring our computation to different infrastructure. Each of these impacts processing and result quality. How will we know if we have reasonably coped with change? One is through processing timeliness, that results are consistently delivered on time and our identifiers for entities are stable over time. The other is processing effort. If the cost of accommodating change is proportional to the value of the change, then we have coped with that change well. And most changes should flow through the system with no intervention whatsoever. And we want this system to be stable over the years to decades that the system will be in service. What is our workflow for processing change? The workflow for processing change is the same as the workflow for applying our models in the first place. We have versions of the different steps of this workflow that are delta aware, and then some steps are delta unaware. In this section, we won't talk about most of the steps that are delta unaware because they are performed exactly the same as was described in part 2 and part 3 of this series. Delta aware pre-grouping. So pre-grouping, as described in part 2, is the way that we identify and process obvious matches. We receive a delta of source records. This may be an entire new data set. This may be add, change, delete requests for records in one of our existing data sets. For pre-grouping, we're going to compute the groups for all of the records in the delta. This may involve retrieving an existing copy of those records for deletes where identifying information where the grouping columns are not provided on the record in the delete. We're then going to reprocess the groups in the delta, all of the groups in the delta. We are not clever about this. We're just recomputing the entire group. We recompute the entire representative record for that group. We could, in theory, be clever and compute how the delta would change a group, but in practice, we find this unnecessary. It is quite efficient to retrieve the group and reprocess it and compute a new representative record. This does require lookup by group key, which adds an additional index and increases the cost of pre-grouping. The output of delta-aware pre-grouping is a delta of representative records, that is, add, change, and deletes on representative records. Delta-aware blocking and pair generation. We receive, for blocking and pair generation, that delta of representative records that we just produced, and we're going to compute the blocks for all of the representative records in the delta. The same as for a delta of source records, we may need to retrieve the representative records we may need to retrieve a stashed copy of a representative record in a delete in order to identify the blocks for that representative record. Then we're going to reprocess all of the blocks in the delta. Again, this is not clever. We recompute all of the pairs for the entire block. Blocks tend to produce redundant pairs, that is, different blocks will find the same pair of records as potential matches. And this process of reprocessing all the blocks in the delta will rediscover the redundant pairs across the changed blocks. One thing in particular that happens here is when a record is deleted, it will be deleted from all blocks and it will vanish from all pairs in which it participates, just naturally by reprocessing the blocks. Reprocessing entire blocks will tend to produce a bunch of redundant pairs. These are pairs that are not changed. They contain two representative records that are unchanged. Those can be filtered out in post. This does require lookup by block and by pair, and that increases the cost of pair generation to maintain those indexes. Finally, we produce a delta of pairs, that is, added, changed, and deleted pairs. This brings us to delta-aware clustering. For delta-aware clustering, we receive that delta of pairs, add, change, and delete requests for pairs, and we identify all of the clusters mentioned in that delta of pairs. We're now going to reprocess all of the clusters mentioned in the delta. This is, again, not clever, but it's a little bit more complicated than processing groups and processing blocks. We need to find all of the pairs that mention records in any of the clusters mentioned in the delta. We're going to retrieve all of those pairs, many of which will be changed, many of which will not be changed in the delta. And we're going to reprocess all of the pairs in all of the clusters impacted by the pairs in the delta. So this is kind of an expanded footprint. We take the delta of pairs and we expand it to all of the pairs in the clusters impacted by that delta. And now we're not going to be clever. We're just going to recluster all of those pairs. We apply the same clustering algorithm described in part 3 of this talk and recluster all of those pairs. This will miss ripple effects as we're clustering just the pairs mentioned in the clusters in the delta. There may be transitive effects that would happen if we did a full reclustering. In practice, the incremental reclustering, the delta reclustering, gets the vast majority of changes, and then periodically we want to do a full reclustering. We might do that on weekends or once a month. This does require lookup by both record and by cluster, but those indexes already exist for survivorship, so we're not increasing the cost of performing clustering. This produces new clusters for impacted records, and that new clusters is effectively a delta of records, add, change, delete on records, and many of those changes are changes to the record to cluster mapping that we produce. Next is survivorship. What is survivorship? The challenge here is to find a previous and next version of the same cluster. As just mentioned, in clustering, we ran an independent clustering for all of the pairs that were impacted by a delta. We now have a new set of clusters. We need to figure out which of the previous clusters they correspond to. There are some standard methods of doing this. The most common method is to use identifying information in the cluster. That is, I'm going to use a name or a taxpayer ID or a DUNS number in the clusters in order to line them up. But this is an entity resolution exercise in itself. And we would like to do something that is simpler than a full-on entity resolution exercise to align clusters. There are algorithms that will modify clusters. Given a clustering and a delta, they will modify clusters in order to keep track of the clusters. These are horribly inefficient and they do not scale to hundreds of millions of clusters, which is what we have. We have a different approach, which is to use set similarity based on source record keys. We observe that records, those source records, are uniquely identified by the source system from which they come and their primary key in that source system. So we can track record identity all the way through our workflow. And a cluster is a set of records. So a cluster contains a bunch of unique IDs within it. We can compute set similarity between clusters using these unique record IDs. This is a Jacquard similarity. It's pretty straightforward. And then given those cluster similarity metrics, those cluster overlaps, set similarity metrics between a previous clustering and a next clustering, we can find an optimal assignment to propagate IDs from one generation to the next. How do we do cluster alignment? We have a previous generation, not just for deltas, but anytime we run the flow, even if we're running a full baseline, every cluster that we generate has a unique ID. We compute this ID using UUID in order to support parallelism so that we don't have a database sequence as a bottleneck on parallelism. When we publish a clustering, we save the membership. That is a record ID to cluster ID mapping. We just mentioned this in that cluster delta publication. For next clustering, we compute a fully independent clustering. As described in the delta processing, we're giving all new cluster IDs, but the record IDs are unchanged. Likewise, if we're processing an entire baseline, we compute all new cluster IDs, even though the record IDs are unchanged. And now we do this alignment. We're going to compute the set overlap. We do this using unweighted Jacquard similarity. That is, we're not considering edge weights in here. We're just looking at the number of overlapping record IDs between a cluster in the previous clusters and the clusters in the next cluster. And this is an O of n operation, n in the number of records. Now we need to use that set similarity, the cluster similarity metric for ID propagation. This is an assignment problem. It is an example of a combinatorial optimization problem, and the bad news is that a fully correct naive implementation of this has complexity big O of n factorial, which is horrible. The largest factorial ever computed is factorial of 170. Not 170 million, not 170,000, but 170. And now we have 300 some odd million clusters that we need to align. An n factorial complexity algorithm is simply intractable. The good news is there are approximations that we can use. And in particular, for any bounded error, we can have a bounded error maximum weight matching approximation that is linear time. So we in fact, don't even need tight error bounds. We find that an error bound of about 10% is plenty to handle this situation where the data is modeling real-world entities, and we're trying to track the data representing a real-world entity over time. It's not enough just to find change. We need to understand the change. One of the really important tools for helping subject matter experts and data consumers trust the output of the system, and in particular, trust the survivorship and trust the reclustering of the system, is giving them a user interface to review change at scale. The delta of clusters may be large. For that 5 million record change on a 500 million, we may still see order of 10 million changed clusters because of ripple effects. And it's really hard for a subject matter expert to review all of it. So what we want to do is give a powerful change review user interface that allows a subject matter expert to filter by the type of change and add a delete, a value change, a record that moved between clusters. This is kind of a visual data diff tool. I can look at my previous clustering, my next clustering, and how they lined up and where records have moved in between those two clusterings. This is powered by that survivorship algorithm and that cluster alignment, and we can do this at full data scale. We've got either a database or a search engine on the back end that allows the subject matter expert to quickly navigate the change and look at what the system is doing in between these two generations of the data in order to understand what has changed. In viewing that change, it's possible that a subject matter expert will notice errors. Some of those errors are systematic, and we can put in a systematic correction. Oftentimes, a subject matter expert wants to just fix the problem and move on. In order to fix the problem, subject matter experts, we give them the ability to durably edit clusters, which is essentially allowing them to say, put this record in this cluster. Survivorship has now given us durable cluster IDs. So this is in effect telling the system the ID of the cluster that that record shall have. And then as successive generations of clustering are produced, those human labels, those human alignments between records and clusters become overrides to the machine learning clustering. A subject matter expert can provide a partial specification because these cluster IDs are durable over time. When the subject matter expert puts a record in a cluster, it's assigning a cluster ID. Other records might also be assigned to that same cluster by the machine learning. So the human user does not need to fully specify a cluster. They can provide a partial specification. To do this, we need robust survivorship and durable cluster IDs. And then on the bottom, you can see an example of that user interface providing a drag and drop interaction to merge two clusters, which will in effect give all 14 records in that merge cluster a permanent assignment to that cluster ID for Alan Thompson. Once we have reconciled all of our clusters with the delta, we come to consolidated records. Consolidated records itself is delta unaware. It receives the current records with the record to cluster mapping. It could be smart and understand the delta in those records. In particular, there are changes, there are deletes, and there are realignments of clustering, and it could figure out just what it needs to recompute in order to be smart about that. In practice, we find that consolidation is not a bottleneck. Implementing this would require another index. It's probably no problem, but it's not a bottleneck, so we just haven't implemented that yet. And the output here is an updated consolidated records. Consolidated records, like clusters, need review at scale. A subject matter expert wants to look and see how have these changed. And similarly to clusters, a subject matter expert wants to make durable changes. There might be systemic changes, systemic corrections that they want to make. Oftentimes, they just want to fix a value and move on, publish that new value as a point correction to the next version of their data product. Subject matter experts can look at the consolidated records, and we give them a user interface where they can see what value is derived from the rule, whether there's an existing manual override value, and they can edit that value or add a new one. This rides on the robust survivorship and the durable cluster IDs. The ID of a consolidated record is the ID of the cluster from which it is derived. That brings us to the end of the change processing workflow. How do we know whether we have succeeded? Let's look at some measures of success. One measure of success is what we presented in part 1, which is that the delta runtime is reduced by 2/3. So we have a 1% change, which is 5 million records, against a 500 million record baseline. Processing the entire baseline takes a little less than 3 hours. processing the delta takes a little less than 1 hour. So we've saved an enormous amount of time in processing the delta. The second measure of success is that IDs are stable. And we have seen stable IDs in hourly production runs for multiple years. That is, we create a new clustering every hour. We do that cluster alignment. We propagate the IDs to the next generation. And those IDs, an ID identifies a stable entity for years. That's hundreds of thousands of runs. And this is in the face of data change, schema change, model change, rule change, manual edits, everything you can throw at the system, those IDs are stable. This is the end of part 5 and the end of the series. In this part, we talked about delta processing workflow, survivorship, visualizing change, and making manual edits. And for measures of success, we looked at the delta runtime being reduced by about 2/3 and our ability to provide stable IDs across years of hourly runs. I'm Nick Bates-House, Chief Architect at Tamer, and I hope this series has been useful to you.